by the sphere is A, right? And we know that the potential at A, if the potential at infinity is 0, the potential at A is given by 1 over 4 pi epsilon naught Q over A, right? So I can rewrite this equation. I can write it as Q equal to 4 pi epsilon naught A. Okay, and concept of capacitance is nothing more than a consequence of superposition. We see this all the time. The fact that Coulomb's law satisfies the principle of superposition, right? Every time you double the charge, you double the potential. Or the other way around, you double the potential, you double the charge. Right? And the capacitance is defined, in this case, the self-capacitance of just a conductor, right? In this case, it's a sphere, is defined as the amount of charge that you can hold at some potential, right? Okay, so in this case here, C for a sphere is given by Q divided by V. You get 4 pi epsilon naught A. So the capacitance depends on the dimension of the conductor. Okay, and in this case, it's a linear in the radius of the sphere. The unit is called farad, and it's basically Coulomb. It's not quite obvious how to see what the shape and the size. Coulomb per volt. We talk about Coulomb, this is from Coulomb's law, and volt is the unit of potential. But if this is part of the advantage of using a CGS system, that in the past we talked about EMNing, and in CGS the capacitance here is just A. Okay. There is no 4 pi epsilon naught, so capacitance is a unit of a linear dimension. But in our case, in MKS, make sure that you multiply everything by 4 pi epsilon naught. Okay? So that's self-capacitance. Next thing is conductor capacitance. This is a more common example of capacitors. Your canonical example is a parallel plate. And let's see. And this kind of capacitors is very ubiquitous in a lot of applications in electronics, especially. It's a device that hold charges. And if you study electrical engineering, you can see this a lot. But in this case, we just want to talk about the concept of capacitance for two conductors. And again, as I said, this is the canonical example, two parallel plates. So what you have is, say, minus Q here, plus Q on the other side. So it's a neutral situation. The area of the plate is A. Okay. The separation is S. Okay. And to make sure that we can study this as this is an infinite slabs, then the square root of the area has to be much larger than the linear separation. Okay. And the electric field as you know, is constant inside, and it's given by, the electric field is given by sigma over epsilon naught. And sigma here is Q over A, right? So this becomes Q over epsilon naught A, okay? And the potential difference V, again, is just E times S, right? The potential is just a line integral of electric field over the length, right? And hence the electric field is constant. The potential difference is just E times the separation, right? So this becomes Q S over epsilon naught A. Okay. So let's see. If I look at that expression, let me rewrite it the other way around. Then Q is just epsilon naught A over S times V. Right? So in this case here, the two conductor capacitance, what's normally called, what's normally called capacitance usually, C is equal to epsilon naught A over S. Again, it has a unit of, aside from the epsilon naught, it has a unit of linear dimension, right? This has a unit of L squared, this has a unit of L, so the unit is length, aside from the epsilon naught. Okay, make sure when you calculate your capacitance, you end up with something like this, where epsilon naught times L. Okay. And let's see. If you look at the, it's the same kind of idea, right? With the self-capacitance of a conductor, right? You can think of these as also as two conductor capacitors, where the either plate is at infinity. Right? And in that case, for that sphere, it's not really that good of a holder of charges. Right? I don't know if you read the book, if you read Purcell, right? If you consider a sphere the size of the Earth, where R is given by, what, 6,000 kilometers? Is that correct?
Yes.
Right, then you'll find that the capacitance is approximately 10 to the minus 4. Okay, so in this case here, if you charge the Earth with a voltage of equal to 1 volt, right, then the amount of charge you have is only 10 to the minus 4 coulomb across the whole sphere of the Earth. Okay. A better way to actually hold charges is a parallel with capacitor, right? Because the capacitance goes as 1 over S, right? You can make this S as small as possible. Right? So it's possible to make capacitors, usually it's in the microfarad. Right? 1 microfarad, and something that size. Okay. Let's see. Capacitor can be used. It's a very sensitive measure of separation. Right? So you can use it as a detector or sensor for position. Right? If I just look at the parallel place, the capacitance goes as epsilon naught to S. If somehow I can carry S, I carry the capacitance. So this is used a lot if, say, your iPhone for as an accelerometer. Because, if you get this thing gravity, because of photogravity, this thing gets pushed closer or farther apart, and then by the variation, you can actually measure the different capacitance. And it's also used a lot if in nanometer positional sensor. here is, again, right, depending on the electronics, you can do it two ways, right? You can fix Q. If you fix Q, right, Q minus Q here, then the change in S, the variation in S leads to a variation in C, right? And what you have is, since a voltage is Q over C, right, you have a variation in voltage. Okay. And you measure that variation. By measuring the variation in voltage, you know the distance change. Or you can do it another way, right? If you somehow fix the voltage, if you fix V is fixed, right? Then changes in C leads to change in the charge, right? And this you can measure. This leads to current, which we'll talk about in chapter 4. Okay. Again, capacitance depends on the size and the shape of the conductor. So in the other two examples that is very symmetrical is when you have the other two examples. They're all standard examples, right? If you have spherical symmetry, then you have two concentric shell. Right? RA and RB. And I'm not going to do this, you can do this at home. You'll find that the capacitance is given by 4 pi epsilon naught times divided by 1 over RA minus 1 over RB. Okay. Divided by 1 over RA minus 1 over RB. And if you have a cylindrical case, symmetry, right, then what you have is this is the homework number I think 59. Right, if I have a coaxial situation, two cylinder, one RA, the other one RB. Okay, I didn't write it down here in my notes, and I don't remember the answer. But I think the capacitance goes as again, some limit epsilon naught times log of RB over RA, something like that. Right? Don't quote me on this. You have to do your homework. Your homework, you can find the capacitance of this object, and I think I'm missing something, right? By principle of superposition, this thing has to be, if you double the charge, you double the voltage, and this thing should be linear in the line. Right? So you get a result like that. Okay, but I'm missing a factor of pi or 2 or whatever. As you see, different configuration, different shape, different geometry, different size give you different capacitance. But that's the idea. Okay. Questions so far? Because it's been especially quiet today. Question? Okay. Next thing I want to talk about before I generalize this concept on conductors is to talk about energy and forces on the capacitors. Again, I'm going to use only the parallel plate capacitor as my example, but you can always generalize this to the concentric shell and also the coaxial cylinder, right? Energy. My parallel plates. Okay. Again, if potential difference is V, okay? Then the work, there's an electric field here, right? Electric field. This way, minus sigma here, plus sigma. If I want to move, a charge minus dq from the left side of the plate to the right side of the plate, I need to work, right? I need to work against the electric field, right? Okay. So the work done to move dq from left plate to right. Okay, W, right? It's equal to, we'll do by this right now. It's just Q times the potential difference, right? The potential is higher here, it's lower here, right? Remember, the potential goes as a function of xa 0 as the potential is higher here, lower here. I want to bring dq from a low potential to high potential. And then what I need to do is just charge dq times the potential difference, right? And this is going to be just, I've been using capital difference. Here, q, right? So this is just dq times the potential, but the potential from the definition of a capacitance, right? The potential is Q over C, right? So this is Q over C. Let me rewrite this. Q over C, right? And I can build these capacitors by integrating the work from zero charge difference to a build-up of a charge of minus sigma and plus sigma on the other side. Right? So the total work and is equal to the integral from 0 to q, right? Okay, q dq over c, right? Sorry, I've been using q everywhere, and then you use this because this is a variable. I'm going to use q prime, right? So when you integrate this, you get 1/2 q squared, q prime squared over c from 0 to q, right? And you get, the answer you get is 1/2 q squared over c. Okay? That's the work done to bring, so if you have these two conductors here, right? You're bringing charge q from the left side to the right, from the left plate to the right plate, so that you build plus q here, and you're left with minus q on the other side, right? And the total work done is 1/2 q squared over c. That's the work done. Okay. Let me erase this part here. And that work done equal to the increase in energy, right? Work done is equal to the energy. Change in energy. Stored in C. Okay, but you're starting with 0, right? Your starting point is 0.
Why is the work done positive?
Because you have to say you already have, suppose you already have minus q here, plus q here, right? Okay. Right? So you're halfway in the process. Right? So there's a potential difference. The potential is higher here, lower here, right? And there's an electric field going that way, right? So if I want to bring charge plus dq from the left plate to the right plate, I have to work against the electric field. This is work done externally. This is work done by you, not work done by the electrical force. Right? Maybe that's what you asked. Right? So this is the work done by an external agent on the capacitors, right, on the plates. So that work done has to increase the electrical energy, right? So this becomes just U because the initial energy is 0, right? So U then is just 1/2 Q squared per C. Okay. Or it's sometimes also expressed because Q is equal to C times V, right? Because Q is equal to C times V, and you can also express U as 1/2 C V squared. To express this. Okay. So let's calculate the expression for the energy stored in a parallel with a capacitor. If I use this equation here, which one should I use? Let's use the bottom one, okay? C is epsilon naught A over S, right? And then V is let's see. V is just E times S. Okay? Right? So then my energy becomes 1/2 epsilon naught A over S, right? Which is the capacitance, right? Times V squared. V squared is just E times S squared. Right? And this becomes 1/2 epsilon naught, right? One power of the S cancel that S. So I have E squared times A times S. Right? And this is this volume. This volume of the parallel plate capacitor. Okay. Area. Yes. Okay. So this is an agreement. You have to make sure that everything is, everything makes sense. Everything is in agreement with everything that you learned so far with electrostatic. Remember, we have a different way of accounting for the energy. Electrical energy is equal to, if you remember this from a few weeks ago, 1/2 epsilon naught E squared. Okay. If I just take the square of the electric field, right, and then integrate everywhere in space, that will give me my electrical energy, right? And this is consistent with that. Okay. All the energy inside the capacitor, right? The work that you do to build this capacitor is all stored in the electric field inside. It's just 1/2 epsilon naught E squared times the volume. Okay. Question so far? Interesting. You look intense. Question on this? No? Okay.
Wait, I have a question.
Yes.
Volume, like where is the volume? If there's like two parallel plates, is
Yes.
it like the space between them? Is that what?
So I'm considering these parallel plates, right? So this all, of course, this goes to they don't go to infinity. They're limited. It has a certain area A.
Yeah.
In the separation. Yes.
So is the volume the space between the two
Yes,
plates?
The volume
Okay.
is A times S, right? The electric field is constant everywhere. Right?
Is it
In- inside the
three-dimensional?
parallel
In
plate.
is this three-dimensional?
Yes, but it's three-dimensional.
Okay.
Yes, the A is the area, so this plate goes like that. Right? Two plates, separation. It's S and we have A. Okay. So, of course, here, if this is finite, right, there's a French effect here, right, that the electric field at the edge is no longer flat, But I'm ignoring that for now, right? So if A is much larger than S, square root of A is much larger than S, then I can just disaffect small, and I can just ignore that, right? And then the energy is just E squared times the volume. Okay? So again, the work done leads to an increase in energy, and the external work here, right? So this is the force. Work is just W is just equal to force times dx, right? This is just equal to d, right? This is the same expression. So if I take this plate, right, if you do nothing to it, right, this plate will collapse onto itself, right? Because of the attraction between plus K and minus K. So something mechanical has to pull it apart, right? So some agent has to pull it apart, right? So you have to apply force to pull it apart. And if somehow the force is doing work, then that work will lead to an increase in energy, right? So here then in this case, F is just u dx, okay? By the way, we know the forces, right? You don't even have to calculate it this way, right? You know you can do this, right? But you can also look at the Newton's law on the capacitors, right? And find the force, remember? We did this before. The force is equal to, I have a parallel plates, right? Suppose I fix one end, I fix this end. Okay. I have to hold this apart, right? There's an electric field, right? So there is a plus Q here, right? So the force is just half of the electric field, right? I don't know if you remember this. You did this. This is also part of your problem when you're looking at the last problem. The last problem in homework 3, right? Where you're looking at the electric field as a whole, and you find that this is equal to half sigma over epsilon naught, right? Which is half the electric field here. The electric field everywhere else is sigma over epsilon naught, right? So this electric field leads to a force on that patch over there, right? And the force is just dq times the electric field, and there's a factor of a half here.
How is that related to this?
Oh, I'm just saying that this half comes from there. See, I'm really confused. Maybe I don't explain it so well. If I have a parallel plate, or if I have some slab, right, some surface, right, with sigma in there, right? There is an electric field. There is an electric field discontinuity. You know that E2 minus E1 in the normal direction is equal to sigma over epsilon naught, right? The force on this patch, the force per unit area, right, is given by 1/2 of E1 plus E2 times dq, or times sigma in this case. This you can prove in many ways. There is one proof offered in Purcell. I think I did a different proof in one of my lectures. And then you, of course, you did this also, right? And you find that factor of half. Okay? So then the force here is a half electric field times Q, right? Okay. Okay, and this becomes E is just, and E is equal to sigma. Sorry for not writing all over the place, the electric field is sigma over epsilon naught, right? And sigma is Q over A, so this gives you force to be equal to 1/2 Q squared epsilon naught A, something like that. That's the force. That's the force on a parallel plate. Okay. And my point is that this force is just the derivative of the energy, right? If you look at the expression of the energy, what can we erase? Energy stored. So here, right? If I look at the expression of the energy, U is equal to 1/2 Q squared over C, and force is P. If you differentiate the energy with respect to X, the separation between the capacitors, you will find the same force. You will find this force F. So in this case, again, everything is consistent. You can calculate force as a derivative of energy change, right? Or you can just calculate force from Newton's law, right? And the answer is the same. Don't just take my word for it. As an exercise, for a parallel plate, calculate the derivative of energy with respect to X, then you'll find that. In fact, it's very easy, right? U is just 1/2 Q squared, and C is epsilon naught A divided by X, right? This is just 1 over C, right? If I differentiate that with respect to X, then I can just say 1, and it's just then equal to 1/2 Q squared over epsilon naught. So again, everything is consistent here, right? The force times the increasing separation should give you the increasing energy. You can think of it as you apply the force to separate the plate farther apart, you're adding volumes of E squared, right? That leads to a higher, larger potential energy stored. Let's see a lot of faces. Question? No? You guys see what I mean? If I have these parallel plates, right, there is already E squared A, right? And I do work on it to separate the capacitor further apart, so now the separation is of S is S plus delta S, right? So I'm adding an extra volume here, right? So you can store more energy, electrical energy in here, right? So the work that you do leads to an addition of electric field that leads to an increasing potential in the electrical energy stored.
That's like when you compress the sphere, right?
Yes,
Or
yes, yeah,
introduce
correct.
new
Yes,
electric-
yes, like that, yeah. I think you gave that example. Question? So with all this, now you know how to do the other 3 problems in that homework. Because it all has to do with the energy stored and forces on a capacitor.
The ones that are due or the ones that aren't?
The one that I'm moving to homework 7, right? So I'm still giving you the extra time to do it. So since chapter 4 is kind of short, so I'm going to lump that 3 problems with homework number 7. Okay? So that's it. Most capacitors that you encounter in practical application, right? They're all 2-conductor capacitors. Right? Usually they have shapes of something like this, and then you hold it into like something like this. Right? You take a sheet and then 2 parallel sheet, and then you roll it into a small volume. Most capacitors are like that. Right? But I want to generalize this into to anti-vector capacitance. In this discussion here, this is the only thing that you have, right? Parallel plates, and the potential at infinity is 0. But in most practical application, right? A few things here. A few things that I want you to keep in mind is that, for one, potential at infinity is not. We don't really worry about potential at infinity, right? Usually your capacitor is inside a box, right? And the box has a ground, right? So in reality, the potential equal to 0 is actually finite, right? And very often in electronics, especially when things are getting smaller and smaller nowadays, with your iPhone, right? There's a lot of capacitors in here, right? And also accelerometers and what else? But mostly in your chips, there's a lot of capacitors because this is the device that holds charges, and you have 2 close by, right? So as you can have crosstalk, right? So as you charge one of them, they can induce charge on the other one, right? So we want to be able to study that. So it's not enough to just talk about parallel plates, right? Where this is equal to Q over V, right? I have to be able to talk about many conductors, capacitance, and introduce concepts that leads to an analysis of something like this. Okay. Another example is where can I erase? Another example is from a fringe fact. If I have a finite parallel capacitor, right? Of course, inside the electric field is just constant, right? But at the edge, you have something like this, right? You'll study more of just in the lab, right? So this is a real capacitor, right? And there is no way to control the fringe. When you have something like this, it's not very well defined. But here you can calculate very easily. But when you have something like this is very much affected by the environment, right? So if I want to build, say, a very sensitive detector of position, right? If I want to detect this separation as very accurately and with high precision, right? Then I have to remove the fringe, right? So how do you do that? The way you do that is you actually encapsulate this capacitor inside another capacitor, right? So if I draw it from the top, right, suppose this capacitor looks like a circle, right? Right, there is a lot of fringe effect on the side, right? So I build this capacitor differently. I build another one, much bigger, or can you do down here also? Okay. So in this case here, I actually have to bracket this parallel capacitor with another capacitor on the outside, right? In this case here, then the whole thing looks like just one big capacitor, right? Then the field, at least on this plate, on the plate of interest, is all regular and well understood, right? You're pushing the fringe elsewhere. The fringe is outside. So then here you have one capacitor, and then you have another capacitor, the side capacitor, right? And then you have to be able to understand the crosstalk. Right? So
Are there fringe effects between C and CS?
yes. So if you make this close enough,
Yeah.
right? So you make the separation very small, then you're reducing the fringe. This is done all the time. If you look at capacitive sensor for positional measurement. If you open it up, they all look like this. So this is called the guard. Right? Make sure that all the field inside the capacitance of interest, the capacitor of interest, is all just flat and constant, pointing downward. Right? So we want to do better than just a standard problems and like lower division physics, right? To do that, I have to introduce the capacitance matrix, and this is again nothing more than principle of superposition. If you read principle of superposition in your midterm, you get an A. I can do that.
It's all you're right. Just
Superposition.
and then leave.
All of them.
So I'm borrowing everything that I said here. You can leave if you want. I'm borrowing exactly from Purcell. Right? Suppose I have a universe with three conductors. Let's talk about example. Right? Conductor 1, 2, and 3. You hold this at potential 1, potential 2, and potential 3. And then the box is at potential 0. Right? So there is a solution to the Laplace equation. It gives you the electric field everywhere. It gives you the charges everywhere, right? So when all said and done, you have Q1 here, you have Q2 here, you have Q3 here. Okay? So how do I analyze this problem, right? Okay? So the way you do it is you write this as a superposition. Again, I don't know how to of three things, right? Hopefully this looks the same. One, two, three, 1, 2, 3, 1, 2, 3. Pretend that this is all identical, right? Then suppose I ground with a very thin wire, right? I connect sphere 2 and sphere 3 with the ground. Right, so the potential here is 0, potential is 0, potential here is V1. Right? So in this situation, here, if I look at the configuration A, let's call this A, B, and C. Configuration A, right? Then Q1, the charge Q1, right, is equal to some capacitance, C1. Q1 is proportional to a potential V1, right? And the constant of proportionality is given by C11. Okay. Q2 is equal to C12 V1. Q3 is equal to C13, right? That's configuration A, right? And this is the solution of a Laplace equation, okay? In configuration B, I can ground 1 and 3, okay? Then I have B, and I have again Q1, this is another Q1, is equal to C21, V1, right? So there is C2, C12, V2, right? In this case here, V1, this is equal to 0, V1 and V3 is equal to 0, I only have V2 here, right? So because of V2, conductor 1 will have charge Q1, a different kind of Q1, okay? And conductor Q2 will be proportional to V2, and the constant of proportionality is equal to. Okay, and again, Q3 is C32, right? And configuration C is the same thing, right? Q3 is equal to C31 V1. No, Q1, sorry, Q1 is C13,
configuration 3.
Q2 is C2, 3, Q3, Q3 is C3, C3, right?
Which two are grounded? 1 and 2?
Oh, on the last one, on configuration C is 1 and 2 grounded.
Oh, okay.
Right, so I only have V3. Right? Because of V3, it induced charges on 1 and on 2 and on 3, given by that equation. Okay? So by principle of superposition, all this add, right? Then this become a matrix multiplication. You guys are all familiar with matrices, right?
No.
No?
No.
Okay, but it's very simple. So basically, by principle of superposition, A, B, and C acts, right? Okay, so I'm not going to use matrix. So you can just write Q1 is equal to C11 E1, right? Plus C12 E2 plus C13 E3. Okay? And Q2 is equal to C21 E1, C22 E2, C23. Okay? And Q3 is equal to C31 E1 plus C32 E2 plus C33 E3. Okay, this is the equation, right? You can think of it as a matrix if you want, right? Then you have Q is equal to matrix C times B, right? But this is how you analyze a system like this with 3 conductor. You can generalize this to n conductor, right? If n conductor, then you have this goes on to n, and you have Q1, Q2, Q3 all the way to n, right? And then you can analyze any configuration. Okay? And then this is the cross term. Right? This 3 term here. So basically this tells you if I have V3, how much does it induce charges on how much is the contribution from V3 that leads to charge Q1 on conductor 1. Okay? And hopefully if you actually design your electronic very well, then this is actually this is small. And you're left only with the diagonal term. Right? Something that you can prove, but it's actually very difficult to prove, is that Cij is equal to Cj I. So this term here is equal to that term. Right? Oh, the C is just a constant of proportionality, right?
So it's just the capacitance that each one.
Yeah, there's a cross capacitance, right? So if I look at this configuration, if I somehow ground conductor 2 and 3, I introduce V1 to conductor 1, right? Then it will induce charge Q1 on 1, it will induce charge Q2 on 2, and it will induce charge Q3 on 3. And all the constant of proportionality is given by something that I introduced, right? This is called the coefficient of capacitance.
Why is it that you don't have to take into account like the capacitance between the conductor and like the wall?
I'm setting that equal to 0, right? You could do it that way too if you want, right? But this is the infinity. This is the reference.
Oh,
right. So I don't care so much about what charges I have on the at infinity at the wall. Okay. So actually, I don't have time. I was hoping to finish it with an example. But I don't have time. But you should go through the derivation in Purcell that talks about just parallel capacitor inside a box, right? And it talks about all the capacitance coefficients, right? And then when you take the limit, the wall goes to infinity, then you get back your standard two conductor capacitors here, where you have epsilon naught A over S.